Morning, everyone. I think we've got enough people that will make a start. Again, leave the door open in case anybody else wants to walk in. Again, leave it open. Yeah, if anyone else wants to walk in after 10-15 minutes, that's fine. So welcome to our tutorial session. Thank you all for joining us this morning. Over the next 3 hours, we're going to introduce you to a system we've developed around working with our marine and atmospheric composition data in a data proximate way. And by that, we mean we're going to try and move our processing near to our data sources. We're going to talk through a lot of different aspects of cloud computing, and then we're going to get you spun up on our system so you can do some testing of some various applications we've got that are focused on using our marine and atmospheric composition data, both from our Copernicus data catalog and from our mandatory program data catalog. And if you don't know what those are, I'll explain a bit about those more in a minute. If you want access to this presentation a bit early on as I go through, then that QR code will take you to it. I'll share it again at the end so you've got access to the PDF version on your phone. By all means, just go at whatever pace you want. We will kind of like take it relatively slow at the start. Most of the first hour, we'll kind of be talking to you in an interactive way, and then the second and third hours is when we'll focus more on the actual demonstration part, when we'll actually get our hands dirty with the data and start to test some things. So before we go any further, just see if I can do this. There we go. Okay, so this is the rundown of what we're actually going to cover today. There's going to be 4 or 5 different parts because we put in kind of an introductory part at the start. We are now in part 0, the introductory part. For the next 15 minutes, I'm just going to introduce us, ask you guys to introduce yourselves, and then I'm going to give you a short introduction to EUMETSAT and our role, our programs, our missions, and our data. Then we're going to move on to a Cloud 101 session, which my colleague Julia is going to present, where we're just going to discuss some common concepts around cloud, kind of try and clear up any ambiguity you might have. I almost certainly guarantee that some of you in this room are more cloud aware and kind of cloud informed than us. So this is an opportunity to share knowledge as far as possible. Where you have perspectives, by all means, feel free to share them. There will be a Q&A session and a feedback session at the end where we can, talk through some of the points of the demonstration. Then my colleague Armagan is going to talk about our setup working across multiple cloud systems. We'll have a short onboarding session, which hopefully will only take like 5 or 10 minutes, where we'll actually get you onto our system. I will be sending out via email credentials to access the system before 9:55 when my colleagues are presenting. So watch your emails for something coming in with access creds. And then after that, we're going to do just data stuff. So we're going to go through short demos introducing our marine and atmospheric composition data focused examples. And then we're going to turn it over to you after coffee for a little over an hour to do whatever you want with the records that we've prepared for you and you've got available. They're built to be somewhat adaptable, so by all means go, explore, test. We'll talk you through what we've got and what you can do. Following that, we've got a short Q&A and feedback session at the end. I'm going to close the door. You cannot leave until you give us feedback. So I've done this a few times at EGU before, and everyone's like, yeah, 12:10, I'm off. No, you're not. That's not happening. So I'm going to make sure you're here till the end, because you don't want to leave at coffee, because all the good stuff happens after coffee. Okay, so moving on. Let's start out with introductions. Who are we, who are you, and who are EUMETSAT? For those that aren't up on the Wi-Fi already, the passwords and the account are there. That'll crop up a few times if you missed this one, but I'm going to move straight on. Small notices. We're there in 0.95. You're all here, so you found it. Bathrooms are just outside. I don't know about any fire stuff. As far as I'm concerned, someone will come and tell us if there's any alarms. We're not expecting any. Coffee break is from 10:30 till 11. I believe it should be set up just outside here. Otherwise, we're in this room the entire time until 12:30. So first, who are we? Who are the people who will be presenting to you today? There's 3 of us. There's myself. I'm Dr. Ben Loveday. I deliver the Copernicus Marine Training Service contract for EUMETSAT under contract. I'm a physical oceanographer with a background in both numerical modelling and remote sensing. I work extensively with EUMETSAT's marine data, both from Sentinel-3, Sentinel-6 and JSON-3, as well as the contributory missions, and a little bit with the downstream products that come from the Copernicus Marine Service. I am the marine data specialist for this tutorial. So if you have any questions about any marine data that EUMETSAT provide, then I'm the best person to ask in this room about, the nature of that data, working with it, access, etc. And if you want to reach me, you can reach me at that email address, or you can find me on Twitter there for anyone who's not left Twitter already. I'm going to briefly pass the mic over to my colleague Julia to introduce herself, and then on to Am again.
Hello, good morning to everyone. My name is Julia Wagemann. I'm the atmospheric composition training manager at EUMETSAT, so I'm the pendant to Ben, just for atmospheric data. And yeah, I will be part of the tutorial specifically for the atmospheric composition data examples and workflows we prepared for you. And now I hand over to Armagan.
Yeah.
Morning everyone, this is Armağan Karatosun from ECMWF. I work as a cloud computing engineer there. I am mostly focused on cloud infrastructure and how we can lift and shift applications to the cloud environment. In this session I will be supporting the multi-cloud DAS cluster that we built for the POC and the presentation. So if you have any questions regarding with how we set up the environment and how we build it in the first place, you can always ask to me. You can contact me from this email and also from AR Karatosun from Twitter as well. Thank you.
Okay, so that's us. And if you've got any questions about cloud or atmospheric composition data or marine data throughout, then you know the people, hopefully, that you should ask. Now, the next thing is, who are you? And I think there's enough of us to warrant doing this because I don't really like going around the room in ones-on-ones because it takes up quite a lot of time. We've set up a small Padlet map you can access through that URL. That should take you to this map implementation where you can drop a pin, and on that map, just put a little pin wherever you're from and just write me a short bio about who you are. Gives an opportunity for also the other people in the room to know a little bit more about you. They might not know anything about you because I think we probably are the only people that got the list of people who were attending. So I'll give you 2 or 3 minutes and then I'll open up the screen and we can see who pops up on the map, and then I'll come back to you after that. Okay, so thanks for adding those. It gives us a little bit more, yay, someone who's a little bit further away. Hello, Madrid. Nice to have you added, Ricardo. Tell us a little bit more about you, and you can click through these at any point if you've got a couple of minutes and see who else is joining you in the room, and maybe you'll find that you have some kind of collaborative overlap to kind of do a very bit of extremely light networking at the start of the day. So that's who we are as individuals, and that's who you are as individuals. And the last person we've got left in the room to introduce is EUMETSAT themselves. Can I have a show of hands? Do you know who EUMETSAT are already? Okay, so I'm going to do a short overview of the organisation and what our rationale and remit is, and then talk a little bit about the data and the programmes that we're involved in. So EUMETSAT's the European Organisation for the Exploitation of Meteorological Satellites, a somewhat accurate but historical name. Now, I've got people sat in the back of the room that are going to be listening to this like quite acutely, so I've got to be a little bit more diplomatic than maybe usual. We're located in Darmstadt in Germany. We were founded in 1986. We have 30 member states, so shown in the map on the right-hand side, all the countries highlighted in blue. And historically, we're best known for dealing with data for weather and climate, thus the name of the organisation, meteorological satellites. And indeed, this is kind of one of our main purposes, probably our single most important purpose, is to deliver operational weather data to our national member state organisations, and then that's disseminated to the public at large via the services that they operate. Now, when I say operate, I'm talking about the operation of satellites. So I'll get to that in a moment, but one of our core kind of focuses of the organisation is the operation day-to-day of satellites to make sure that everybody, which includes all the cloud data providers that disseminate our data, have access to it on a regular basis. However, since EUMETSAT's inception, we've also taken on other roles in other big European Commission programs, the most obvious being the Copernicus program, under which we deliver data for a various number of thematics, including marine and atmospheric composition, and also operate satellites on behalf of the European Union under the Copernicus program. So here's an overview snapshot of the missions that we currently operate. And by that, it means that they are flown from our operations room in our building. We divide these into three kind of segments. We have our mandatory programs. These are our historical, current, ongoing, future developing programs that are responsible mostly for providing data that are associated with weather. There's really two platforms. There's the METEOSAT platform, and then there's the METOP platform. The METEOSAT platform is a geostationary platform, and the METOP platform is a LEO platform, meaning that it runs in an orbit that kind of circulates sun-synchronously. We have optional programs that are programs that have more of a historical legacy, but we've taken on some of the control for. JSON-2 is no longer flying. JSON-3 is currently flying. It's an altimetry satellite, and we disseminate the data for this as well as operate the satellite. And then we have the Copernicus program, under which we operate a significant number of satellites, and it's continuing to grow as we move into the future. So if you are aware of the Sentinel-3 or Sentinel-6 satellites, we operate those. We also operate Sentinel-4 and will operate Sentinel-5 on board the METEOSAT 3rd generation and EPS-SG, EUMETSAT Polar System 2nd generation satellites for atmospheric composition, weather, and a whole raft of other applications. And in the future, we'll also operate Crystal, Simmer, and the follow-ons for both Sentinel-3 and Sentinel-6. So we operate the Sentinel-3 satellite. For those of you working in the marine domain, that means that any of the data that you get at some point has gone through our ground segment station and is actually disseminated somewhat complicatedly by different organizations, and I'll come to that in a minute. So we're busy, and we're not getting any less busy. We are picking up more missions every time, every decade, every iteration of a program. We tend to operate more and more, and as we move into the 2020s, 2030s, we'll be picking up some of the Sentinel next generation missions as well. Our data is processed by two different sets of people. We have our satellite applications facility, which is a distributed network of experts across Europe. They generally focus on the data that comes from our mandatory program satellites. So that's everything from METEOSAT and everything from METOP. There are eight SAFs. So and each SAF deals with a specific, when I say SAFs, I mean satellite application facility. Each SAF deals with a specific type of data for a specific purpose. The one, for example, that I most usually engage with is OCSAF. This is the Ocean and Sea Ice Satellite Application Facility. That works with any data from our mandatory programs that has a relevance to either the ocean or the cryosphere. So, for example, sea surface temperature data from AVHRR would fall in this. Any winds that come from ASCAT would fall under that remit as well. And we have different SAFs that focus on atmospheric composition, climate, numerical weather prediction, for example, all under these kind of thematic hubs that are based around that, the geography that's shown on that map. We also have our role under the Copernicus program. Now, the Copernicus program, the European Union's Earth observation program, is broadly divided into three different segments. We have a space segment, we have a services segment, and we have an in situ segment that sometimes people forget, but is of critical importance to the kind of operation of the entire thing, as it allows for satellite validation and model validation. So we generally operate under the space component, so we operate the missions, as I previously said, and we also take the responsibility to operate some of the coordinating missions. The landscape gets a little bit complicated here in terms of where your data comes from. So under EUMETSAT, we operate Sentinel-3, we operate the entire mission, but we're responsible for disseminating the data for marine and for atmosphere. Any Sentinel-3 data for land is processed and disseminated by ESA. Anything marine at all, despite of how you might see it labeled out there in the world, comes from EUMETSAT. It is not ESA Sentinel-3. It is EUMETSAT Sentinel-3, and for marine data, it's 100% ours. So if you've got any questions about it, wherever you find it, we're the people you come to. Okay, and then the same thing is true for JSON-3, Sentinel-6, and then when you want to work with data from Sentinel-1, Sentinel-2, Sentinel-3 for land, for example, or this host of other missions, those are all operated, the data is disseminated by ESA. So it's a little bit complicated, but if you want to know specifically where your data comes from in terms of who's the satellite operator, you can come talk to me. This feeds downstream into the Copernicus services. Those are aggregators of data from multiple different sources that take in, satellite information from various different platforms, pull them together into usable products that are more easily consumed by the community, be they experts or more anecdotal users. For example, Copernicus Marine Service, the Copernicus Atmosphere Service, C3S, the Copernicus Climate Service, all take our data downstream and they all ingest data as well from the in situ part of the program too. So the Copernicus services are a common place for you to go to want data that's what we would call level 3 and level 4. Is there anybody here that doesn't know what the different satellite levels mean? That's a bit unfair. If it's level 1 and level 2, it's single mission, usually, on the instrument grid, the fundamental types of the data. If it's level 3, it's level 4, it means lots of data from lots of sources have been usually merged together on a common grid to either do some sort of gap filling or give you a longer time series or bias correct. That's the kind of data that tends to come more from the services themselves. It's quite thorny where the overlap is, but I'll happily discuss that with anyone who wants to. That's the first part. So now you know who we are, we know who you are, and you broadly, in very quick terms, know who EUMETSAT are. Do you have any questions before we move on to the more cloud-focused part of the demonstration?
So, where do you, or in which platform do you integrate the level 3 and level 4 products?
So, I'm not sure what you mean by platform. Do you mean cloud platform?
Yeah.
So there are different ones for different organizations. So under our mandatory programs at EUMETSAT, level 3 and level 4 products would fall under the European Weather Cloud, which is our internally federated cloud system, which is mostly for access for our member state Met services. We're going to use that today. For the marine data and some of the land and the atmospheric data, usually that would be done by the Copernicus Marine, Atmospheric, and C3S services. Those have access to our Wekio DIAS Copernicus Cloud Platform. We're also going to work with that today. So our data can end up anywhere, but those are the two that we'll focus on through this demo. The short answer, well, the long answer-ish, is I can't tell you where all the data is because nobody's really mapped it.
All right, thank you, Ben. Okay, good. Now we come more closer to why we're all here this week, to cloud and cloud services. Just a quick survey in the room. Who is more like a user of the cloud? Okay, and then more like a cloud administrator and... Okay, good. Because as Ben said, like there is probably some of you have much more technical knowledge on clouds. My part will be now more on the perspective from users. What does this also mean? Working on the cloud, getting data in the cloud, and also moving entire workflows to the cloud. And then Armagan will more bring the technical aspects. Good. Sorry, this is... Okay, good. So like the current situation is that, yeah, we have, like from the user perspective, it's not always quite clear, right? Like what to use. There's like a big fragmented landscape. There's also different levels or types of clouds around, from more pure clouds like the Amazon Web Services, Google Cloud Platform, but then also there's in Europe a lot of activities on community clouds like the European Weather Cloud or Wekio. Then there's also more platform approaches. You might have heard about Google Earth Engine or the Planetary Computer. But definitely cloud computing is a paradigm change, not only for users, but also for data organizations. And this is probably also one of the results why we have this fragmented, diverse data landscape we have at the moment. It is also a very extremely fast developing domain at the moment because there's like new packages, new formats, new specifications like Stack was quite agreed by the community within 1 and 2 years and is now widely adopted. So yeah, there's like a lot going on. Sorry, I have to... But what can cloud actually give us for users, but also data providers? And so cloud is a chance that we actually can process and access large volumes of data because we have petabytes of data already available, and this is just growing in the next years. And we have new data, and the cloud gives us then also new data access methods and formats. So that allows us to chunk the data in smaller parts, and then we only request what's actually needed, for example. Then the processing, and this is also focused today a lot on our tutorials, data locality, so that we can process the data where they sit, and we don't have to move a lot around, and basically we just moved in the end what we need, the final result. And then, of course, there's also opportunities to have to go serverless and to have dynamic resources. So this means also that we can create and throw away resources quite fastly, and we can really flexibly adapt it. Good, but so the overall paradigm, it's that we want to bring users and their analyses to the cloud, but it is really pushing many of us probably out of our comfort zone, because as we are used to analyze data, so we download data, we work on our local computer, this is a paradigm change, and we also have to learn and adapt how this actually works, and it's also a different mindset. And now I want to ask you to go to Slido and want to ask you, in what zone are you? So if you remember, we have here comfort zone, fear zone, learning zone, and growth zone. And the Slido we prepared for you is hashtag EUM-multicloud. Okay, so it seems like we 100% all in the learning zone. So we already passed the fear zone, and it's more like that we have now curious interest in what's coming up. So that's good.
I was in the fear zone, but I was too fearful to write fear zone.
Okay, so,
so I put myself in learning zone.
At least you admit it, so maybe it's also the same case for others. Okay, good. There's also even one probably or two in the growth zone. That's good to see. Good, we have another question for you, just to also get a bit of a better understanding of how you work with clouds. And I now activated the next question. So what cloud platforms do you know of? Oh, okay, Wiki and European Weather Cloud, okay. Or was it Ben? Okay, so far Wikio is clearly the winner here. Okay, now AWS. Okay, so now we're getting closer to this this landscape of clouds available. Okay, so we have another, and then now even more popping up. Okay, our next question is, which of these cloud systems do you already have experience with? And we gave you a list of cloud systems.
I just need to fix this one. Yeah, I'm about to fix that now. Apologies for that. You can now select as many as you like.
Okay, again, Amazon, AWS, and Wikio. Okay, Google Earth Engine. Okay, big winner is Amazon Web Services, but followed by Wikio, and then probably Google Earth Engine. Okay, good. Our next question is, what do you consider when selecting a cloud to work on? And we gave you 6 different options. No, 7, sorry. Okay, price, and then, oh no, now the first is data sets available on the system, followed by price, and then scalability. Okay. And then our next question, which of these tools' data formats are you already familiar with? Okay, cloud-optimized geotiffs are the clear winner. Object storage, okay, Dask and SAR, not so much. Okay, so this is actually good news because we will also have a focus on Dask, and also in one of the marine examples, you will work with SAR data today. So there is something you can try out new then. Good. And then what currently limits your use of the cloud? Okay, knowledge, to not knowing where to actually start. Price, time. Time because it needs an investment to learn how it works. Okay, price. Firewall. Difficulty onboarding, okay. Documentation, data, so not the right data is there. Knowledge. Okay, excellent, thank you. And now, sorry, this is now the, no, this is the last one. So basically, before today, were you already aware of EUMETSAT's marine and atmosphere data streams? Not quite sure. Okay, a bit, no. Okay, so you will learn a bit. So those who weren't aware, you will learn quite a bit on the data today. Okay, good. So then I try to finish off with the rest of the presentation fairly quickly. Okay, thank you, Ben. Okay, so basically Good. So I will just give a short overview on first the importance of cloud optimization when it comes to serving data. So why do we have cloud optimized GeoTIFFs and SAR and these new data formats? And then a short aspect also on data locality, so what it actually means and why we also do it, because these are the focuses of our tutorials and the practical part today. So why do we need cloud optimization? So we have a higher latency with remote access, and it allows us just simply to fetch more or also the right part of the data with fewer reads from the cloud. And it is an efficient data access because, because even with the modern fast networks, it's always not a good idea to move more than we actually need. And it's often that a lot of analyses is that we want to do the analysis on long time spans, long time series, but in the end, we actually only just interested in the time series. But in order to come to this time series, we need the full time series and data stream. So it also reduces the application of data because access a single file online instead of needing to copy and catch the data. So we access the data where they are instead of moving them. And there is a need for optimization of data access for either parallel or partial reads of the data. Okay, I probably do it this. Okay. There's a nice graphic. This just has been published by the Cloud Native Geo from Radiant Earth about different formats of cloud optimized geospatial data. So our focus is less on vector, but more on raster and data cubes. And so the traditional data formats, we have HDF5, NetCDF, GRIB2, GeoTIFF, and basically now the most common ones, what you also all share today, is cloud optimized GeoTIFFs, but also SAR is picking up quite a bit. And these are the two most common formats used at the moment for Earth observation data. So cloud optimized GeoTIFFs, I think you all worked with them already. So it has a specific internal structure of the more traditional GeoTIFF files. It has an internal file directory which tells the client where to find the specific information from the imagery. And it also allows for internal tiling for having quicker access to specific image regions. And it also allows, or it is structured or it's providing different overviews of different zoom levels for quick rendering of large volumes of data. SAR is a storage format that allows to store large n-dimensional typed arrays. It chunks the arrays in n-dimensional parts along any dimension. So even beyond 3 dimensions, it allows to chunk data quite efficiently. It reads and writes arrays concurrently from multiple threads and processes, and this is also one of the drawbacks of SAR, that it stores the metadata separately, so it can quite blow up the SAR data format compared to cloud optimized GeoTIFFs. Good, data locality principles. So this is, so our focus today is also the comparison of data proximate and how we can do this with DASC compared to if we don't do a data proximate computation. And the principles of data locality is that despite our wish list of having a unified data landscape or just one data access where we can access all the data, this will probably not happen, and we will have many different data access points on multiple locations. And so the question is how we can actually solve this to bring different data sets together. Federation is one option, but the distance where the data comes from and lies is still, it will always matter. And the input-output speed at the location of the data will always exceed any network speed. And so if you have any data, so if you have a chance to process the data directly where they are, it will always excel or exceed compared to moving data to another place. And then there's often, as I said already, like there's a lot of operations where we need a lot of data, but in the end, the result is actually just like some kilobytes. And so we have to think of having the data intensive or the processing intensive part, bring them to the data and operate there, and then just move the final result. And then Dask can help us. So Dask is a framework that is quite often and familiar and quite often used in the Earth observation community, but there's also other frameworks that exist. Dask supports multiple forms of data locality. We also linked you to two blog posts here where you can have a look at. We today, in the examples, we specifically use the Dask pool names patch, which has been described by a blog post from UK Met Office and Dask. And this is an experimental or a pilot piece of work. But in the end, the idea is to have a more automatic and simpler method and suitable for specifically Earth observation examples. So how does this work? Sorry for the full slide, but you will see this soon in practice. So the principle is that we assign a pool resource, or the workers of the cloud, they are assigned to a specific pool resource during the creation, like for example EUMETSAT or Wikio. So the workers, we assign them to a specific pool. And one provides the relevant pool label when opening a data set. So basically we say then, okay, this data we want to open from this pool, or this data set we want to open from this pool. And then this label is then propagated through the entire task graph, which Dask is setting up, so through the entire processing. And once we hit run, so once we say to Dask, okay, now we want to compute, then these tasks are placed on the actual workers with the matching labels. And then the Dask manages for us like which workers are working and processing our data. And so on the left you see the principal code example here, but we in all our notebooks have the same these examples how we can set it up, and you will say this. So you see this later. So basically on the second step we define the pool where we want to say, okay, we want to open this data set from this and this specific pool, and then we prepare our computation. So we say, okay, this function we want to run on the data, and then in the last step with propagate pools we actually execute and start the computation by itself, and then the workers get active. Good. So this was now more the perspective from users, and also what we will do and you all will do today to try out and play around with data proximate computing. And now I will hand over to Armagan, who tells you all about the pilot system that has been set up for today.
Hello, everyone. Yeah, okay. So we will talk about a little bit in depth on the infrastructure side and how we did things in the cloud. So actually, Ben, if you want to mention about this slide, you can, if you like.
Yeah, I can do. So we've referred to this before already. So today we're going to be working with two different cloud systems. We're going to be working with the Wikio system, and that's going to host all of our Copernicus-focused data. And then we're going to be working with the European Weather Cloud. That's going to be focused on all of our EUMETSAT mandatory program data. So we're going to work in a data proximate way. We're only going to process Copernicus data on Copernicus resources. We're only going to process mandatory program data on EWC resources. And then as required by the processing graph, we'll bring them together only at the point where we've minimized the data that we have to transfer.
Yeah, thank you, Ben. So if we just move forward with this, I want to give you a brief history about why we started with this in the first place. So the question was simple. We were actually getting talk with the UK Met Office, and their question was, as we just been talking about, and on is the multiple systems that they have and the multiple data sources they wanted to access. So they were already using some kind of a cloud infrastructure in their own processing, and they also had access to European Weather Cloud. European Weather Cloud is actually a federation between two cloud entities, which has ECMWF and EUMETSAT resources. So the question was that, okay, how we can process large volumes of data without even moving the data from one place to another. And they were envisaging using Dask and Python to do that, but they also were interested on minimizing the data transfer between clouds because this is very costly. And this should be ideally scalable and portable enough for that you can just plug and play any cloud that you would like to do, because not everyone uses Amazon. For example, you have your internal systems that you might just want to use. You can use them in combination with this tool. You should be, at least. And okay, this has some challenges, to be honest, because normally in a local environment where you run your computation, the network is flat. So you allow actually communication between worker nodes or whatever that you are interested with. So this is pretty much easy, let's say, easier from the cloud environment. But in a hosted cloud environment distributed around multiple regions that you might have, I remember the slide someone was mentioning about firewall. Yeah, this is a big problem. The other problem is the IPv4 addressing conflicts, because you might be using some internal VLANs in your local environment, which might conflict with the public cloud providers or the European Weather Cloud, for example. And nothing in particular, I mean, the NAT itself is quite challenging because it is actually violating the idea of the internet by, okay, in the internet, in the main idea, every device should have an IP address and they should be reachable. And NAT is actually hiding that behind of a complex firewall rules. So this will actually have a performance impact on the processing and access to the devices. And yeah, this was basically the challenge that we need to overcome with. And to do that, we tried a couple of solutions. There is not one clear winner at that time because we need to explore a bit. So what we did, we were aiming to have something this redeployable setup from pets to disposable kettles. Do you know the analogy between pets and kettles? Basically, it means that when you have a system that you have a name on, for example, I have a system called Anakin, and it's Anakin. It's very special for me. I need to care for it, so it's my pet. And I also have a system called Dask Worker 01020 something else. I don't care about those systems at all. If I have some problems with it, I just redeploy it with a next number in line. So this system is like, this analogy means like, okay, you care for your pets, but for the kettles, you are just treating them like a kettle and you just try to process the data like that. So we were aiming to the kettle more in order to make it portable in every cloud infrastructure that we might have in the future. So in order to do that, we had 3 POCs. We built a VPN first, hand-built, it's a pet, to demonstrate this interoperability between AWS, EUMETSAT, and ECMWF cloud infrastructure is possible. So we need to, first of all, make sure that this is happening. And then this was like one VPN hand-built in every cloud so that it will allow communication. And the second part, we were just try to make it a little bit more redundant with a mesh VPN setup. Mesh VPN setup, if you don't know about it, it's like a star topology. So in the first hand-built VPN system, you have one VPN gateway, which is the bottleneck of the system. So every communication goes through, it will go through this VPN gateway, and it creates a bottleneck. In the mesh system, you have a star topology where you have multiple VPN gateways, so to say, that can reduce the communication bottleneck. And we also, in this phase, did some reusable templates for allowing quick deployment of task workers and schedulers and WireGuard. You can actually see it on the image, on the top image, so that we can allow it as deployable services in European Weather Cloud. Now we have those items as a library items in European Weather Cloud. And the last one, the last POC that we did was this dynamic throwaway fully automatic mesh VPN setup that we will show you today as well. The VPN mesh is automatically created by why you initiate the DAS cluster. So from a user's perspective, you will not be able to realize what's going on under the hood. And details about this work is actually published in various online sources. You can just try Googling DAS multi-cloud and you will be seeing a lot of information about this setup. So actually I want to talk about our implementation a little bit specifically in comparison with the other solutions. Both are coming from Dask actually, but we have a couple of ways to install Dask. And there are this standalone Dask clusters that you can use. There is this distributed Dask, and there is also this thing called Dask Gateway. And what we have done is very similar to Dask Gateway, but has one major advantage. And I want to just make it more obvious in this slide. So in the Dask Gateway on Kubernetes, for example, the core focus is multi-tenancy. So every worker that you created has a dedicated scheduler, and that scheduler is only allowed to talk with the worker nodes that it has been enrolled with. And this is perfect for multi-tenant isolation because every single one of you will have one dedicated scheduler, and in the other cluster you will have another scheduler. But the major problem, and the problem that we were trying to solve, was the communication between the worker nodes between multiple regions. So imagine you have one Dask gateway in EUMETSAT and you have one Dask gateway in VKO. The schedulers that you have on those gateways will not be able to communicate with each other. And this is like kind of an anti-pattern for us and our workloads. We need to share data between these regions. So this is why we came up with this solution, with this resource pooling algorithm. And now in our Dask multi-cloud adaptation, the Dask scheduler will have access to worker nodes in every region, and it will highly favor the node with the local data available. If you don't have a worker node on that specific node, it will obviously schedule your workload in some other node. But if you have a worker node close proximity with the data, it will highly favor that. Yeah. In order to do this, as I told you, this was our main focus. And in order to do this, we developed a custom patch for this Dask worker pool add-on. It was kind of an obvious there. It was enabling us to label Dask worker nodes to have some kind of a labeling in between. So what we did for that is to patch it in a way that we can make it more region aware, so that we can use it in our advantage. And yeah, the multi-cluster communication, you will be thinking, okay, you have two different clouds, two different cloud infrastructure, and you are saying that this scheduler is able to talk with this and this in different region. How it will happen? You don't want to put everything on the internet and expose everything to the internet. This is why we have the mesh VPN in between, so that you can hide the multi-cluster communication through a secure channel, and you don't need to expose everything to the internet, and it can be still relatively secure. And one of the other advantages is that every worker node will know the close proximity to the next worker node, so they will follow a shortest path available for them. Yeah, in order to do this, now I will deep in a bit on the networking side and how we built the mesh VPN. Please bear with me, it is a bit technical, but not that much. I will try to make it like a bit more high level as well. So what we've done is, as I told you, is a star topology. So it is basically a two-level VPN where you have the mesh network between scheduler and the endpoint routers, and you have the star of workers below the route. So you can actually see it on the below image, the topology I mean. And this network structure means that there will be no central bottleneck, which is common in VPN gateways, like I mentioned. If you have one VPN gateway, every communication will flow through it, and if you have something going on in there, it will be become an issue for you. And this routing of the workers allow them to place it deep into the cloud, which basically means that you will not care about IPv4 subnets in your cloud infrastructure and in your local infrastructure on premises. So it will give you an advantage of having a separated VLAN. And this is actually the next bullet point. Every Dask cluster has its own internal network, so that they will not rely on the subnets that you have. It will always get the same addresses inside of the VPN, so it's easier for you to remember which node is where. And it uses IPv6, essentially eliminating the address clashes because it's unique. And it also allows you to adopt a neat internal naming scheme that you can name resources based on region. So you can have an IPv6 IP which points which worker node is in which region. You can have EUMETSAT VKO in the name. So it has an advantage of, if you compare it with remembering 164, 167, 35. And this is, the best thing is that this is reproducible, dynamic, and throwaway. So once you initiate the cluster, it will initiate the VPN mesh as well. You will realize it when you go deep, but you will not realize if you are not careful. And once you take down the cluster, the VPN mesh is gone. So that's also quite neat. Yeah. Okay, so we have some results from the initial POC. You can see at the very end, we did some calculations over NFS, and it took like 15 minutes and transferred like 3 gigabytes of data. This was a small calculation, but when we do the distributed calculation, it just took 10 seconds and 8 megabytes. So this is quite a difference when you do it with the multi-cloud adaptation. We also checked a couple of possibilities. You can read about all those things in the Dusk blog post because this work is actually published there. And yeah, I mean, from the numbers, it looked us very advantageous, so we need to move on, doing more. And this is how we built the next gen being this implementation of the training that you will attend. So I must say the hosting a training environment is hard from an administrative perspective. I am the admin of this platform right now, and it's just mind-boggling how big it is. We are hosting shared Jupyter Hubs instances for you that you can log in, and you will have access to remote workers in European Weather Cloud and VKO, as we were mentioning, and which every user will have one dedicated work node in both platforms, which makes basically this amount of vCPUs and this amount of RAM. And if time allows, we want to run one single calculation to benchmark all the cluster, but this is very neat. And what's new today? I want to continue. So what we did to improve the system, we actually built custom container images to make it even more portable. So theoretically speaking, you can get those container images and deploy yourself and build your own cluster, which is quite neat. And we also hide a lot of complexity behind with the simple startup scripts. Before that, it was like you need to still know your way around, and now it's a bit more automated, and we hide a lot of things behind of the screen magic so that you don't realize. And the biggest improvement is that we have now multi-cloud and multi-user, meaning that in the initial POC, we only aimed for one user, spawning one Dusk cluster, and then take it off. Now it can support multi-cloud and multi-user, and it has an authentication mechanism that you can enroll it with your internal system. So this is more future-proof. And from the infrastructure perspective, we built the infrastructure as an immutable mindset, which means that it can be teared down and built up from scratch in a couple of minutes, which fits really well with the cloud adaptation. So it gives you like pay-as-you-go. It fits really well with the pay-as-you-go model, so to say. It is cloud agnostic. You will have the source code available pretty soon, so you can just try it with your cloud in Amazon, Google, or your internal systems. And it is just providing the building blocks, so you can actually combine it with your other scripts if you have them. And there and back again. So we did all these POCs, and we realized a couple of things. What we realized mostly is that it is possible to distribute work efficiently across multiple systems while still keeping the existing workloads. So I know the learning path of cloud is quite hard, and we wanted to make it as easy as possible for the end user to not realize what's going on in the backend. So this is a major benefit that we have. And our approach compared with the others is actually significantly hides the networking complexity with this automation and everything. It presents the user an identical system where they can just deploy, tear down multiple times, and this will always be the same cluster and the same approach. The identity and authorization mechanism is improved, and you don't need any other identification sources inside of the cluster, which reduce a lot of complexity if you ever just deeping down to this authorization business. Examples might be exchanging the SSH keys or exchanging the VPN credentials. And it's highly portable. We informally tested this implementation on Amazon Lambda for serverless, and it should be straightforward to implement it on Kubernetes as well. So this is fairly portable, and it will allow you to actually improve it a little bit more. I have a couple of acknowledgements. I want to thank Mike Grant because he did a lot of work on the code rebase, and he's unfortunately not here with us. But he did a lot of work to make it a more cloud native and portable. Credit to our colleagues in NetOffice because they also did a lot of contribution on how we can name these pools based on the cloud proximity. And our fellow European Weather Cloud pioneers, mostly Vasilis Pausis and Rupi Tarvo, because they put their heart in it, and this is possible with all this combined effort. And I think my slides are ending here. Thank you very much for listening. If you have any questions regarding with the infrastructure, I'm available. You can always just come up and ask something if you have them.
Okay, thank you, Armagan and Julia. That is the end of the complicated hour where we talk at you. So everything from now is going to be more practical. We're going to get you onboarded on our system, and then we're going to start to run some demonstration examples of working with our data. So we're just pulling together a list at the moment of all of your credentials, including the walk-ins who signed up. I think we're missing a couple of people, so we might just do a little bit of a round robin onto the room, just to make sure we've got everybody. Then we're going to give you your accounts, log into our Jupyter hubs, and then a couple of other little keys that you will need to work with our data. I'm going to quickly show you what onboarding looks like, and then we'll make sure that everybody is up and running and spinning, and then we'll introduce you to our notebooks after that. So this is going to be a bit fun for me. I'm going to sit down for this one because I need to work at my computer at the same time. So before I launch into that, can I see a show of hands who's coded in Python before? That's what I want to see. Who's used Jupyter Notebooks before? Okay, no problem. For those of you who didn't raise your hands, don't worry about it. We are going to show you how to do it anyway, and we have plenty of time over the next 2 hours to do it one-on-one with you to kind of familiarize you. Okay, so I am going to just open up my browser. Ooh, oh, it's already open. Fantastic. Bear with me. So I can't quite figure out my screen arrangement. And I'm not mirroring, so I can't see what I'm doing. Okay, let me just turn around slightly. Okay, so you will be given one of 3 URLs to get to our hub. They're just called Hub 1, 2, and 3. I am going to log in on Hub 01 for me. You will do exactly the same as what I am doing now. You won't be able, don't follow this URL just yet because some of you will be assigned to Hub 2 and some of you will be assigned to Hub 3. You will get an email in a minute telling you which hub you are on. So we span out 3 different instances of Jupyter hubs just because it's a bit easier for us to manage. Okay. When you spin up your hub, you'll be asked to provide your access credentials, also coming by email. And when you do, excuse me, provide them, this will bring you to this, our Jupyter Hub environment. For those who've not worked with Jupyter, this is the standard landing page for a Jupyter Hub. From here, you can do lots of different things like run Jupyter Notebooks, use tools or use terminal commands or make text files, for example. When you arrive, there should already be a folder called multi-cloud on the file manager on the left-hand side. In this folder are all of our test notebooks for the demonstration that we will run through today. Okay. So as soon as we've sent out this email to you, you need to navigate to this multi-cloud folder, and we'll help you with that in a sec. And then if you click on the index file that's in here, this will give you an overview of everything we're going to do in the next 2 hours, including links to other material, the notebooks that are available for you to work with, and links to any other bits of code that we are going to tinker with a little bit today in terms of setting up our cluster. Now, at the moment, we don't have a cluster running, and we're going to talk through examples of how you actually get one up and going and how you actually connect to it in a sec. Okay, so while we are sending that out, I'm going to show you quickly on this system how you bring up your cluster. And it's extremely easy. It's going to key straight off your user account details that we're going to give you. So when you log in, it's going to assign you in the background a couple of workers, one on each of our, well, more than one, on each of our different cloud systems. So it's just a little bit of kind of clever system trickery we're doing in the back end, basically linking you to resources by your username. So in order to spin up our cluster, we need to open the terminal. And all we do from inside the terminal is type cluster start, and that is it. So it's going to go away now, and it's going to find, associated with your username, the IP addresses for your workers on both the European Weather Cloud and on Wekio. Again, do you want to talk a little bit through what it's actually doing here?
Yeah, sure. I mean, yeah. Okay, I mentioned in my slides that we are hiding a lot of complexity behind, and this is a lot of complexity behind, if you want to see it. And this is basically what it does. It recognizes your username and the credentials in order to create these key pairs to allow you access to the VPNs in between. And it basically then initiates the cluster. In your local hub, it will initiate a scheduler for you, a task scheduler, and in the remote cloud nodes, let's say, it will initiate the worker nodes. You can actually see what it does. It creates a worker nodes associated with your username. It also creates something called router. This is related with the VPN mesh that we built. So once you initiate that, this will basically build, and you can see, okay, maybe I can use this. You can see it creates an IPv6 subnet. It's actually coffee, if you pay attention, but it can be anything else. It can be like EUMETSAT, Wekio, or something else. So you can actually do something smart there to see which worker node is in which cloud infrastructure. So, yeah.
So from a multi-cloud perspective, the key part is we've set up these two different sets of pools. One set of pools we've tagged with this for EUMETSAT to run on the European Weather Cloud, and the other set of pools we've tagged with Wekio to work with Copernicus data on the Wekio DS system. So we now have one cluster with two sets of workers that are on different clouds. Now, we're going to use these names, Wekio and EUMETSAT, to assign pool names to our data to make sure they run in the right parts of the system before we bring things back together on our hub to do any analysis we want with the resulting data. So we're just going to now send out an email to you with credentials. Hopefully you're getting them. If you don't get them now, then tell me, because I might have missed you.
So I just sent it. So please, if you haven't gotten an email, then we have to double check the email addresses.
As soon as you do get the email, feel free to click on the hub link and try your username and password, and you should be entering a Jupyter hub that looks just like mine. I'm going to put the mic down, hands up. If you have any problems, we'll come run around and make sure you're all okay. Send it to you, Julia. Yeah.
Why is this just one question? So how did you deal with user accounts, say, on EWC or Wekio? So did you pre-register users with those users?
We pre-registered them as user 01, user 02.
Okay.
Our original idea was we would use people who signed up, but as you can see, we have 4 more people who walked in, so we decided just to do it sequentially.
So to understand what is needed. So they do this in a completely separate environment with different clouds with the same approach. At this point of having to register the individual users before you have to do before.
Also, I can show you sort of in the back end all it does is there's a file on here that just maps the username to an IP range. So you could just give it the IPs if you wanted to spin up in that way.
No.
I mean the registration, if you're asking about that, like having the users onboarded to the system with a with something like a single sign-on or something like an authentication system, you mean?
Well, that would be the next step. First, I want to understand what to do. Like, if you want to add a third cloud on the Copernicus database ecosystem, you would need user 6 to have an account on the Copernicus database ecosystem. And that you have to currently, the user doesn't have to do that. Go on web page, say register, confirmation email. That is something which, because you don't have single sign-on, of course.
Right now, honestly, actually we do. So every user that we register in the system, so imagine if you want to register your own workloads in Amazon, right now, you can do it. So we will give you this opportunity to run this experiment if you very like to do so. And this authentication mechanism is hidden behind, but it is plug and play. So if you have your own single sign-on systems or own authentication, you can actually pass that information when you are building the system.
But I do have to have this, or the credentials for Amazon, I have to have already, so I need an Amazon user account. You can't create a user account.
Obviously, yes.
Yeah.
Yes, but the idea might be is that, okay, you have a virtual machine, let's say, running on Amazon, and then you already have a running environment. This will be enough. We don't require you to pass any credentials of Amazon to this system because it's actually a security breach. You should not be doing that. All we need is a running instance in any cloud, and then you can basically hook the system up with that running instance and expand your cluster.
It is magic.
It is a bit magic, yes.
Yeah, very, very impressive.
But how does you not trigger the other resources without getting the credentials? So encrypted credentials like that.
Yeah, you need to authenticate to the virtual machine. Yeah. Now let's be a little bit more specific. It uses SSH to log into the remote systems. So assuming that you have a virtual machine running on Amazon, which you know which you have an SSH key that you can log in with, you can use. This is enough. You don't need to do anything else.
So you provide the key, basically, you provide the key to your system.
What we do is something like this. You have this portable. We have this installer that comes with the system. So you can actually, what you can do, you can just say that, okay, this is my key that I'm using to authenticate the systems. Can you please install this cluster setup to that virtual machine as well? And it will basically do everything necessary in order to initialize the cluster, and then we will be able to use that. So it's just this, an Ansible installer which deploys this, let's say, magic setup. Or if you want to do this manually, you can create an SSH key, you can create a user there, and you can just pass that information into the cluster subset. This is a bit more, let's say, hands-on approach.
But what do you need for me then, in the simple approach, still an SSH?
Yes, an SSH key basically.
And no. So assume now you have resources on pay-per-use tab, create years or something. I guess it works the same. And you also take care then of spinning up, spinning down.
Yes. Which tokens? Like application credentials or?
Yeah.
This depends on the backend that you are using. If you have something like Kubernetes, for example, as a backend, it will be possible to authenticate to Kube API with a token. But if you have, if you want to use a virtual machine, for example, there is no. I mean, you can only use SSH key-based authentication or username and password, which I highly discourage. So the only valid option would be an SSH in this case.
Okay, so I think with one exception, everybody has made it onto the Jupyter Hub, and if you haven't already run cluster start in your terminal, then you can do so, and this should give you something very similar to mine, where you get a load of registering of these workers setting up, and you get some assigned to Eume and some assigned to Wekio. Has anybody not managed to get quite that far yet, or is still waiting for a cluster to come up, or isn't sure how to launch one? Still waiting? Okay, it'll take a few seconds. The workers haven't been used this morning, so they're just, they've had a nap. They're just coming up now. Okay, so we have 10 minutes until we have our coffee break. So in that 10 minutes, we're going to give you a very, very quick overview of the notebooks that we've got available for you to work with. And you are free to use any of them in any way that you wish. On the marine side, from my perspective, I have 4. The first one describes the data that we're using. I would encourage you to go through this one because you'll also be receiving an email with a key and a secret to access some of this data. You can add this in this notebook. The second one, which is really not part of the narrative but is just for your interest, is on benchmarking. Basically, how does our data approximate workflow compare to how you would actually perform that if you were having to bring that data to your local system in order to do it. And the other 2 are on marine-specific applications. One is on heat waves in the Mediterranean Sea, and the other one is on more physical oceanography of the Alboran Gyre, looking at eddies. I'm going to quickly look at the first 2 to show you an example of how you would run a notebook if you've not done so before. And I want to show you some stuff with regards to DAS connecting to the cluster, because it's quite interesting. So in 1.1, if you click on 1.1, this will open your first Jupyter notebook. For those of you who've not used Jupyter notebooks before, they're just very nice ways of bringing together code and a load of other design scaffolding that helps you to learn about what code itself is doing. There are essentially only 2 different kinds of information in here. There is code and there's everything else. If it's in a little box and it's got grey background and it has a little set of square brackets next to it, it's code. Otherwise, it's not code. So this first example walks through telling you all the data that you're using. It tells you where the data location is. There is an example here that's on AWS. It shows how to access that data, but really is just like a benchmark for how you use S3 buckets. We use that to build one of the products that we use extensively in our demonstration. If you have any questions about any of the data that aren't explained within this notebook, then you can ask me. So this notebook just shows how you have access to this data. If you want to run a Jupyter notebook, and if you've not done so before, at the moment, because they have little numbers next to them, they are pre-run. If you go to kernel, restart, and clear outputs of all cells, this will remove the run state of this notebook. If you then want to run something, when you read down, have a read through the different parts. If you get to code blocks, you can either click on the little play symbol at the top to run it, or you can quickly just hit Shift Enter. This will then run this code block. If you really want to, you can run it all from the start by doing restart, kernel run all cells. This notebook will fail if you do that, because at some point it will ask you to provide authentication. Now I'm just going to skip down to this authentication part because you'll be receiving an email with some information you need to enter in there. So I've already run this cell. Let me just run a few more. This one. This will make a little widget. All you do is you take the information you receive by email, the keys and secrets for EWC, and then you hit Create Auth File. That will make an authorization file that will work for all the rest of the notebooks here. You will never have to do this again. Okay, so this is the first one, just does your authentication for everything else. Now I can do on mine, because I've already made that file, I think, restart and run all. And it should find my credentials file. And now this will show you how we access our data. This is you working from a standard S3 bucket on AWS. This reads in the Sentinel-3 Level 2 SLSTR sea surface temperature products as cloud-optimized geotiffs. These are single tiles. We've then mosaicked those into individual daily, well, to be careful here, individual tiles that span the whole Mediterranean. So we've aggregated the orbits, we've mosaicked them, but only for nighttime. We've then also got the data from our AVHRR Level 3 product. This is our mandatory program data. This is drawn in as ZAR. And then for the Level 4 product, we've got the C3S sea surface temperature product from the Copernicus Marine Service, also as ZAR. Now, irrespective of if they are cloud-optimized GeoTIFF or ZAR, we have put them in X-array data arrays. So we've used different ways to feed the data into that, and I'll happily discuss with them, but we're working with data arrays across the board because they're all then immediately Daskified for multi-cloud kind of use. That's number one. Number two, I'm going to just touch on, because in number two we actually use the cluster. Number one does not use the cluster. In number two, it's just for benchmarking. Basically, how well did this perform running on our hub versus running locally? Running on our hub with data approximate computing is the blue. Running on just the hub itself is the green. They're not that different because our hub is still quite close to our data. Running locally is the orange. So there's a non-linear fade away for if you were to perform these processes locally or you were particularly distant from the data. So we're going from a paradigm where we're working with this, which would be really, realistically, if you were working on any cloud system but the data wasn't proximate, this is what you'd be looking at in terms of downloading it to local and working with it, to this. So there's a significant improvement in performance. I encourage you to read the warning box, but what I want to quickly do here is I am just going to run this in a data proximate way. Data proximate equals true. And the reason I want to is I am going to then make my Dask client under here. And this client gives me information about the number of workers that I have available and where they are. But nicely with this new implementation of Jupyter Hub, if you click that button up there, that little magnifying glass, you now have access to the entire Dask workflow as it runs to see the processing graphs as they occur. So if I restart and run this one in its entirety, and then I click on task stream, then with a bit of luck, once this is up and running, so it's just reading in the data now here, just from Wekio in this case, we can see the Dask processes actually run as they go. So we should be able to see, when we're running in multi-cloud, which workers are doing which jobs and where. And you can use that throughout.
You can bring it in one.
You can actually bring it in one window if you want to see your notebook and your task stream at the same time. Then you can just put them side by side.
We will still have access after the presentation, or you will stop the credential at the end of the presentation?
At the moment, you're working on very, very happily, freely provided cloud resource. So we can talk about your desire to be a beta tester. None of the resources that are available here are per se completely closed. They just aren't free. So yeah, this is a prototype system that we're building at the moment. So yeah. To point out, none of what we're presenting here is proprietary to just our cloud systems. All of this can be run and has been run with the UK Met Office on AWS. So, you know, if you have other cloud systems you want to exploit using this, then you can.
Yeah, that's what I wanted to ask you. If you could show us how we can integrate our own resources.
I actually put that in as a workflow and then took it out because I wasn't sure if we'd get that far. But if you want to focus on that, then maybe we can have a look at doing it. Armagan is definitely your guy in terms of setting up access to other things. Like you said, we've done it with AWS. If we've got the IP ranges and then we can see the workers, then maybe.
We can catalog if the time allows. And about using the system, it all depends how much coffee that you can bring to me.
Julia, do you want to do a brief?
Yeah.
Sorry, it's cool.
No, that's fine. Yeah. Okay, so I think we're all in their need of coffee. I just want to quickly show you as well, if I can. Okay, so Ben, the entire system or the entire examples, they work on the same access credentials. So you see what Ben showed, the marine examples, and then here under the folder atmosphere, you will see 3 notebooks. And also in a similar setup. So the first notebook gives you an overview of 3 different data sets that are available on these 2 cloud systems. Maybe I just close this here. Or maybe I just, yeah. So you can have a look. They should be quite, okay, now it's even, I moved this here down, yeah. They're quite self-descriptive. So we have data from Sentinel-5P tropomi, carbon monoxide values. Then the other example is on METOP from EUMETSAT's polar orbiting satellites, and specifically the GOM2 instrument, which with the data from this satellite we can create level 3 absorbing aerosol index products, and this is a good tracer for wildfires. And these 2 notebooks, who are the workflows, they feature specifically the Canadian wildfires that appeared throughout the summer. And I don't want to take too much from the coffee because we have another hour once we come back, and then we can go through it. And if you have questions, then we're all there, Ben, Armagan, and myself. Okay, then we see each other again at 11.
Guys, for the next session, we're just pretty much going to let you run however you wish, and if you've got any questions, come and ask us and we'll help.
Sounds perfect. Cool.
So maybe also like you
Oh,
can
yes.
have like these windows of the task stream and also the workers side by side with the notebook, because then if you run a notebook, then you really see workers spinning up and.
I could watch dash graphs all day.
I
It's just loading the data. And then as soon as it gets to it. I lost my cluster.
When the cluster is running, the dashboard should be available without adding any URL, right? Or do you have to add any?
To bring up the side stuff, yeah. All as soon as you hit that create cell, then you hit the icon. If you run the whole thing from the start, then
Okay,
it can't. It can't get into the process to bring up the dashboard. It's a bit of an annoyance, really.
Okay. Because I was wondering if it is my computer network or not. That's
No. It's it'll be just the dashboard itself
It
can't.
might be my network as well.
Okay.
So, no worries.
is this the firewall?
Yeah. That's why I brought 2 clients.
Oh yeah.
Let me just see. I think. Let's just take mine down. Okay, workers. used to run you. Ah, no wonder.
Pretty much from already when it started, like when it came out with IPython, like 2014 or something with notebooks, yeah. But specifically this system, this is really fresh, so this has just been set up for bits now as a pilot in the prototype. Yeah.
I'm going to kill our hub if I'm not careful. I just realised I did something silly. Sorry, I'll wait till everyone's back.
You just joined, correct? Or
Yes.
yeah?
Hi guys.
We can, so, because it's the second part of our tutorial, but we can give you a short introduction and then you can then also try out
There we
the
go.
cloud system, what we prepared. Because this will be now more like the next hour will be more explorative.
Okay, and you already introduced all the theoretical part of it?
Yeah.
Yeah.
Yeah. Yeah.
You're welcome to stay and play
Yeah.
if you want to.
I mean, during the next hour, everyone will be just trying.
Yeah, there will be you will be able to log into the same system what you see here. We prepared some workflows with Copernicus data, and then you can try out a Dask cluster. You see how the workers are computing the different, executing the different processing functions. Yeah.
Does that make sense to you? Okay, what we just said, like vocabulary-wise, you understand about Dask, and you probably catch up okay then. Up to you guys. Just come and tell us. We'll have to give you the access credentials, so we'll need your email addresses. But yeah. I realise I've left this one to default run on the hub with 4 workers and 8 gigs. So if anybody runs it, so I need to make sure no one runs it. Yeah. Although actually we have, because we distribute on the hub, we might get away with it.
Yeah. Okay.
All right.
Sorry.
If you are around for the rest of the week, assumedly you are, Ben Loveday, Julia Vargaman, come and find us and ask us if you have any questions.
Thank you.
Okay.
Thank you very much. See you.
Mm. Workers all happily
So
working.
also let us know if there's any questions you have or things not very clear. Ben and I are here, and also Armagan.
If anyone is going to run the 1_3 marine notebook, at the top, or in like a third cell down, there's something that says data proxima equals false. Please make that equal true before you run it. If you leave it as false, it won't run data proxima. It will just make a cluster on the hub itself. So it'll be a bit slower and might blow everything up. Apologies. I love being able to do this. It's fantastic. I mean, next year I'm overhauling all of my notebooks to use Dask. I'm going to have to, like you say, like for stuff like plotting Sentinel-6 or plotting Ultra data, using one core. I mean, why?
Yeah.
Yeah.
No, definitely. And this is the future, right? So like in 10 years' time, it will be only a system like this.
Pretty much. Yeah. Yeah. I mean, even working with 15-minute MTG as well.
Yeah.
massive, right?
Gigabytes
Per,
per
yeah,
month.
yeah, it's
But
massive.
I could load it, right? And
Yeah,
you can play
yeah,
around
yeah,
with it. So it's
Mm. So we're not going to demo anything for the next hour and 20 minutes. So until 10 past 12 or whatever, it's entirely up to you to go and explore whatever you want. And if you've got a range of problems or you've got questions, stick up your hand or shout for us and we'll come to you directly rather than do it as a group. So,
So maybe you would like to also have a setup like this, where you open the task stream and the workers also right next to the notebook, because then you really see also what's happening in the background once you execute something. And if you like, because we believe it's boring us just lecturing notebooks, which also are quite self-descriptive. And you learn much more, like, and if you, but please don't hesitate if there's anything you don't understand with any command, then that's why we're here for.
What was the trick to open that?
Yeah, so like once you have a DAS client, so then once you have a DAS client, then you can go here to the DAS symbol. And then you can go here to the magnifying glass, and then all the orange parts, they coming up. Once you activated your cluster, and you also have a client in your notebook. This is right at the beginning of each notebook. Yeah. So and the cluster is basically you open a terminal and you run cluster _start.sh. And then you can choose basically here the windows. So what we chose here is the task stream and the workers, and we just brought them to the right side panel.
If you want to play around with it, you're more than welcome to.
Just go and read. Hi.
Hello, nice, good.
Yeah, all fine.
I took a couple of photos of you presenting.
Once we do the feedback, I also do some. Sorry, I forgot this.
No, it's fine. It's fine. There's enough going on. Can you do me a favour though? Can you take a
Yeah,
picture of
sure.
faking presenting this one with all its stats and glory?
Okay.
Yeah.
For our credentials, how long will we have access to this, to the environment?
the system's really set up as like as a demonstrator, really, and adaptable to any other place where you have VM-based cloud resources. We think probably with GitHub use. At the very end, I'll show you access to the GitHub where all the notebooks are, some of the cluster setup is, and we're going to start to populate that with pretty much everything we've done in the back end as well. So you can.
So all the notebooks are available.
Oh yeah, all the notebooks are already free. I'll share the access to that. We will leave the data on object storage as long as we can as well. What we won't be able to do is give you the processor, but continue with. There is an example on here also that runs off using parts from AWS, so that we have some compute available on AWS.
Yeah.
Probably relatively easy to have this to run on that infrastructure. So it's translatable. It's handled frequently.
No, it's not user, so I send you another email with the access keys.
Perfect. Thank you.
So authentication worked so far for everyone?
Just because everyone's back here, if anyone running the 1_3 marine notebook, the one on heat waves, if you decide to run the one, just let me know. Because there's some small thing I have to adapt.
That was in cell number 4, right?
Sorry?
In cell number 4 on that script.
Yeah, I think so.
Yeah, from false to true.
Yeah, that's correct. So if you are running the 1_3 marine heat waves one, in step 4, make sure data proximate is equal to true. Else it will just run on the hub with too much resource.
We put our account under stress.
Yeah. Okay, yeah. It depends what sensor you're using. So
How?
Yeah.
naturally,
Do you already have the task graph? Yeah?
I have them all open, but
Yeah. So basically how you do any window is so,
always the red one. A microwave sensor
sorry.
will always pull out
You-
sunscreen by default.
And so basically you can just,
To get to foundation,
okay. You can just pull it down and then Jupyter Hub provides you a proposal on where do you want to have it.
kind of like
now it's
consolidate.
I tried it before.
It's always like this.
Wind speed, multi-band rate of transfer.
Well, just to
some
confirm
motion
some concepts. In Sarai structure, attributes are metadata, variables are the variables themselves.
I can
Yeah,
dig
so
out
I-
details
Or whatever we are.
Exactly, like these are the
and also time and solar geometry as well for the radius of
parameters.
Yeah.
Yeah.
Oh, okay.
Yeah.
Perfect.
And
Yeah, it's-
so
it's
probably
multiple
also like
different
once
arrays as well, so
you,
it's-
there's
it's-
also a difference in X array between a data set and a data array. So like usually once you load the X array, then it loads a
what you
data
hear is
set.
it's easy to just
And the data set can be a
really is
collection of different parameters or variables, but it share the same coordinates, dimensions. In order to get then the real data array, so where the real data is, you have to then select a variable of your data set.
All right.
Yeah. And then you have usually attributes on the data set level. So this is channel on your data file when it was created. And once you load a variable or a parameter, then you have specific attributes on your parameter, like for temperature, the unit, and the long name, and so on.
All right.
Yeah.
Perfect. Thank you.
working okay for everybody at the moment? Good. For the marine notebooks, by the way, they're set up to look at specific areas, like the heatwave one looks at the Tyrrhenian Sea. But you can change this if you want. You can look at heatwaves in a different area if you want to. Provided it's inside the Mediterranean, then you can move it around if you want to explore somewhere different. Basically, the entire Mediterranean was a horror show in 2022, so you're not going to not find a heatwave, I'm sorry to say.
Yes, so, well, in order to understand the rules and so, for example,
Yeah.
we are reading.
So in this case, we're only using one pool, one underscore two. So we're only using the wet-year pool because we're loading Copernicus data from our centre for SISTR, SE temperatures and stuff.
Well, another pool could have
But then
Yeah,
you
but
are
I think if we,
spawning the worker accessing the same data.
To work on that data.
To work on the data. But
okay,
the hub also knows about the data.
Yes. You can run all of this inside the hub. Or if you make data proxy equals false, it
Mm.
will run on hub. It will make dask on the hub and run on the hub.
But that means you need, at least for an example, you need the data to be available, like what we discussed, freely on an S3 bucket, freely to everywhere, but to everybody, because
yeah, so
it's
once this
available
is
to the hub, it's also available to the worker.
you just have to set it once, but it's a bit,
Now, assuming that you have a more
it's also for
restrictive
keys
data
to
source,
set it
so
in.
it is only available from that approximate location, I guess you would just do
Better safe than sorry.
different continuums which you then send to the node.
You can use the same
Yeah,
you
well,
can use the same structure.
there's
We have
different
always
levels
to
of
know
openness.
the path. So for example, we are talking
Okay,
with the
now.
S3 online here to get the file paths. If you already know that, for example, in your systems, you can manually
Yeah.
say instruct the hub to go there. Or you can run this instance completely in an isolated environment where you have access the internal resources. Because this can run in your laptop. Right now we are hosting it for you because it is too much of a hassle for you to deal with maybe. So, but you can run it in your laptop, you can run it in your on-premise servers, or you can run it in a cloud environment where you can run it on Amazon, Google, or VK, basically. So,
In this example one for me, I understand what's really doing the calculation on the worker is basically here, the analyzed SST.
No, that's lazy.
That's lazy.
It happens there. Now you'll look, there's two different.
Yes, yes.
Right, I'm using two different ways of calling dask. I'm using .compute. That forces the computation to occur right at that point.
Mm-hmm.
You'd really only do it when you want to have a small output loaded into local memory. Later on I use persist because I call three functions at the same time. Now persist will only run when the output is recalled by any later function. So I don't want to run compute there because I want them to run this one, this one, this one. I want to be able to be ready to go, but called whenever they need later in the script. So, but nothing happens until .compute or .persist or .plot or something where you actually require the data.
And where is func defined?
Func is there. So as I was saying, like,
Func,
func
okay,
can be
yeah.
as complicated as I want. As long as I don't need to evaluate it, then the dask magic happens only in that box. So that's your function.
So the analyzed SST cell,
Yeah.
that could be a function which is, in the extreme case, which only makes sense at a specific worker because it uses paths which are only available there, or even an API which is only available there.
Yeah.
So it would be, and doing the Python code behind is sent to the worker.
Yeah.
How is that done?
So this, at some point here, I should be able to retrieve, I haven't managed to do it yet, a full dask graph of that computation. Now, creating the graphs is technology of running the computation itself, so I've not been able to do it. But it should give you the map of how it's like connected the dots, and then where it executes the dots. So, yeah.
Yes.
So you're not limited, functions aren't
Ah, yes.
limited to common off-the-shelf boring stuff.
Okay, so have
So
you already initialized your client up there?
Because exactly for that.
Create the credentials. But this is only like the records, right? So this is only showing the data. If you go to one of the other notebooks,
And then,
if you let's open the second book, for example.
and repeating the code.
Here, this one on atmosphere, the center. So if you go down, did you also spin up the cluster, by the way? Did you run cluster underscore start.sh? Okay, so then you have to open a terminal. But it's up. Okay, good. Okay, perfect. So then we go back to the notebook. So this is basically, okay, now we initiate the cluster. If I think this is also just an overview. If you go to this one, for example, you will see that below we will start in some work, a task stream is the one where you really see the processing, and now you can just pull the tab on the right side, for example. So if you go the down here and then more down, yeah. And now you have this overview. And if you go through the ones like right, so and then you see really what is actually lazily done, because with X-array you see that everything is executing, but it actually is just creating the graph. It's just creating, okay, so once you say I shall compute, this is what I shall do. So it's all lazy. And then basically once you hit the compute at the end, then everything you see that the work is just starting. And it's and so basically how you do this, if you go below.
Quite a while ago,
Okay.
everything was done sequential.
Yeah.
And then I find that it's possible that you can parallel
Yeah,
everything.
yeah. And you do it lazily. You first create basically what you want to do, and then just at the end you say, okay, now let's do it, instead of doing it all the time once you need it. Yeah.
I have to read it.
Yeah. Yeah.
Even my Macs are quite cool. 32 gigabyte, and I'm using 1.8 for most of it.
Okay, did you
Because every
launch,
notebook runs on one core.
Very much mine.
So you have to open a terminal,
Yeah, so
and you have to
inherently I want to
cluster
make my stuff so
underscore
simple
start
as
.sh.
possible.
Because if you cluster each tab, and so now you start your work.
It's just a matter of
But you have to wait a
how I
bit.
teach
So
people how to
let's
do
see
it.
the
And then if I do that, and teach them that one,
Yeah.
just not teach
Yeah.
any
Yeah.
scale or
Yeah.
resource. By default.
Thank you, Dan.
But now you get your workers, and then you can also initiate a client. And once you initiate a client, then you can hit the verify class, and then you see the class.
This is why also
You don't,
yeah,
yeah, because there is nothing, it knows what to connect to.
Standing is very heavy numerically. So,
Yeah.
yeah.
Cool. I'm really impressed. Great work. Thank you.
Just trying to understand
For
the last
the,
one.
no, for
So
the,
I am not a DAS expert.
for this one, I think, yes, you will need, you don't need it for the,
We just needed
So the magic happens.
I think,
because I was able to.
this one, yeah,
I was able to.
Yeah. Yes.
Okay, but
No, here, no, this
no,
one,
this
this
one.
one, it's
Yeah,
just
yeah,
the data
yeah.
overview.
Yeah, yeah.
Here you don't do any data.
Okay, so the client at the moment
Yeah.
is looking for that. I've called the tools
Yeah.
UMETSAT because that's what
So
we
now
that's
let's,
what we call
okay, this
the pools
takes a bit.
that are already defined by our cluster externally. And then there's a little library called Propagate about called data approximate workers, which is written by the UK Net Office. It's kind of basis for what we do.
A lot on, more for training, specifically for training.
Working on setting up the clusters, or are you also
A lot for
working on
5P,
data
because it is the
accessibility and
where
yes.
Not here, but it is, but it doesn't wait for the site.
So not directly,
So, no, okay, let me get it.
for
It's
example,
not
we
where
have data from him, because it's processing it as a 3D application.
Yeah.
They are now also part of the
Do you know if there's a way to impressively list all the photos you have on this, or does that not work?
You cannot just list all the files if there's too many, so you have to be able to
That
page it
Yeah.
correctly, but I think both library and Python can, or
And now you can, for example, like, what do you, if you go to the task stream, then you can just pull it,
if you
you
want
can
to
open it as a tab,
that's why
and you
people
can
are also
decide.
combining S3 something JSON based database would work the best, to be honest.
And now, yeah,
Combine it with
exactly.
open source and Elasticsearch, MongoDB, Amazon does it, DynamoDB,
Yeah.
and they build a I created a model, and just build a database to get the list, and then but for this implementation we are actually talking with S3 API to list
but you kind of know where the data is lying, that helps, because if you just start from the lowest, it will really annoy you to, like, I don't know, this through 30 photos or whatever, get there. But yeah, I get that having a database or like an index file really would help.
Okay, so
If you also try to open the tasks
to use
we can see
NoSQL database instead of a database, because this kind of data format is not supported than a SQL-based database like
Yeah, that's good to know. I mean, basically right now it's just using buckets that are already there and accessing the data, but I think they don't have a couple of files.
Once we load the data, it basically does
Yeah, that's why I was asking, and I guess the rest of the
once
data
you tell
won't
me
be
I should
as 3 buckets
then
by
I
now.
can close it, but I actually don't have it in. So even though XRA shows you that, okay, so after this function, our data set will look like this, it is actually not completely get. It's just at the end. Yeah, so here we just initialize our client and we say, okay, we will have 6 workers or
Yeah, that's what I wanted to look into as well. What formats do they use? Because I guess basic concept
if we load these, then these use the workers
depending on what data you have, I guess it's
and
not
but
always
it's
the
not
best,
so if this
but
one
rather
here, it's so
thorough.
if you initialize it, you will not see anything in the tasks tree because it's just basic, it's just creating a graph saying, okay, the data is there and this is the way how I have to load it.
Oh, okay.
Yeah.
But what you do
Exactly. Exactly. Yeah. So then you do like a lot of operations, but these operations, as long as it's on XRA, so any XRA operation, it is all done lazily. So it just as well also remembers, okay, you want me to do this with the data. And okay, I can do this one and the result will be this, but it's actually not computing it. Yeah, it's like a,
I love to use this.
and at the end, with tasks, once you say compute, then you will just say, okay, now follow the entire recipe.
give you a specific case
Yeah.
and we design it.
So, or if you do, so this happens if either you do compute or if you plot. So if you will do like, you loaded the data set and then you do a simple plot, then you will see your task workers start. It's basically plotting is where you need the data. Yeah. Yeah. And so below, there's at some point here, you see basically, so this is probably close, this is the data proximate part, and then with persist is like a collection of functions, what you want to do. And here you will see then your task, your workers start actually doing something. So it's either persist or compute. And if you have a look to
Yeah, from the outside, especially if you have like sensitive data.
How we build this training environment is like as open as possible. We are relying on this approach to work having issues in this environment. We didn't do training session, which will be hard to troubleshoot so that this doesn't mean you can have everything in your system without exposing it to the outside world, which will make it not hack, but someone needs to hack into your system, then they can hack everything behind.
true?
I think it is another folder.
Okay.
My colleague says obviously
Obviously, try to restart and then maybe try to bring the tasks together, because then you can really see when actually the computing starts and what is basic.
Now, this does rely, in my case, on the data on the same dimension.
So how then so that function persists. What is it called here? What other like we said where am I writing the rest to the server?
Okay, but is
And then execute.
Yeah.
How is it written? Like all these functions are just sending the orders and then
Yeah. So it somehow like will between task and X array. Not sure exactly like, but in the end, like once you work with task, then it handles a lot on the understanding.
Is the library?
Yeah, task and X array, the combination. Because in one of the examples of the atmosphere notebooks, there is an example once the function only with X arrays, and this is lazily, so then you don't see any tasks. Once I add that I want to convert the X array into a pandas data frame, then it's already executing it. So it's only as long as you stay in the X array ecosystem that you can do everything lazily. Or once you log, then you also see that data is actually transferred.
It's not updating the data. That's it.
Have a look now to your tasks, please. Because I don't know why I can't see tasks. Okay, maybe we have to ask Ben on these notebooks. No, because this is the cool thing to actually see when you look the server. But go down and let's try to go on persist part. Did we already do the persist part?
Only getting chunks of these.
Okay. And we don't see any tasks.
Because it's a cog.
Okay, we have to ask. Or maybe we can try another.
Yeah, I mean, if you the cloud native chunk has different views of the data anyway.
You can is this in the 5P or the other one is the third one is because this is not any data approximate. This just gives an overview.
Really sorry, but we have a video problem. We have a video conference. You're staying until when?
Wednesday I will be here as well.
Okay.
I guess.
So you have another demo or presentation?
I have one poster presentation tomorrow.
Okay.
That I will be doing, and after that Wednesday I don't have anything particular to do, but I can just talk and link meetings as well.
Yeah. Thanks.
Yeah, thanks.
This is a task.
It's for Sentinel 5P data from molecules per square meters to molecules per square centimeters, which is more common. So now you have your sketchlers.
You see the level 2 then?
So we, for this example, we just converted level 2 to level 3 just to bring all data files onto a common grid. Just to make the processing over to the master. I have to ask what if they, but probably so that they use the proposal.
For my own workflows,
because I work with the level 2 and
From the cloud. So, well, for this example, of course, like, it's massive. But it's also not a how you say, at the moment because it's a pilot, so it's not an official data source where we say, okay, here you can get level 3 data. But yeah.
Okay, and yeah,
So here we just create a subset.
Yes, it's in
Yeah, for Canada.
432.
Yeah, and now we do the visualization, and this is already a part where we should see the task. Why doesn't it spin up?
I'm used to work with ghosts.
Okay.
No, maybe I don't know how apply it here to visualize the.
No, but you have it's the same setup, so
yes.
Yeah, so anyway, so here the topic should basically actually show you some tasks and the work perspective. And then the next step is again like when we create again a function. This one is where we actually bring in level 3 GOM 2 data. And we process a long time series from 2012 to 2023. And we want to calculate a number of pixels above a certain threshold of aerosol, photic aerosol index. And this is a good trace for wildfires. And at the end, you see, no, but if you go just back, just down to the end, you see here how you see here the Canadian wildfires compared to the previous years. And so so this is basically Canadian wildfires. So we select, so absorbing aerosol index is just an index that shows you or gives you information about the amount of aerosols in the atmosphere. And aerosols can be emitted from wildfires. And so anything above 1 is already quite high aerosols that can come through from dust or wildfire events. And so here we selected only the pixels above with an AAI index above 2. And then we calculated the number of pixels. And we see here that like for Canada, we have like this year extreme events. And so if we go below, you see just this is actually a very simple function. So this is below the Canada borders, just to clip the part for Canada. And then this is basically the entire, so this is all X-ray, where we say, okay, please just select the pixels above 2, then count them over the entire area, and then resample it to monthly, and then sum all,
This is the attribute. No, time attribute.
time is basically, we say resampling because it's daily files and we want to bring it to monthly.
Okay.
Yeah. And so if you have a look, once we load the data, it's around 1.2 gigabytes, and just with this function, it will be reduced to a couple of hundred kilobytes. But there's like, it's one line, but it's happening a lot, basically, because it's files it's 1.2 gigabytes.
Great work.
Yeah.
Great work. I definitely foresee us being asked for more demonstrations of this.
Technology, but unfortunately we don't have the environmental
Yeah. So we have not a technology to understand
run through.
Sure.
The bit we need to fill in, as far as I can see, is
Yeah, exactly. Yes. So here the thing is for Gomez, we already have a long time series, so it started in 2007. And for Sentinel-5P, for this example, we only have 2 months of data for Canadian wildfires.
because it means that we can explore
But yeah, so
whatever
definitely we
appears
could do like since
and benchmark it.
2018.
People say, oh, I just made a cloud outside. It's like, great.
Well, of course,
And the answer is usually yes.
if it's
Say
exactly
at large
your
scale,
own,
whether or not it was
where is
Yeah. Yeah.
one question maybe. Is it same here and periodic? Do they have?
yeah.
Periodias, I don't know. So WikView, the data is available. Periodias, I don't know what to do with wrong
No,
information.
I mean, I don't know.
It is not. We have that.
Yeah.
Okay, perfect. So, related to this.
For people to just learn different set of APIs with
I also think that it's now it's the wrong way around. Any API that offers data access in terms of moving data from A to B, I think it's data number.
Another question.
Can't move data.
More related
It's
to
too big.
how do you try to downscale?
for sure that the data is getting bigger with the new instruments that we have.
It's exponential.
It's exponential.
So,
Right now the new
I
one
mean,
we have.
well,
I
here's
still
the
use
all.
when I talk about example.
Increasing the possible resolution
Yeah.
possible with
We have
local with us data.
To grow
You need
Yeah.
income.
Yeah.
more variables.
Exabyte level.
So there's some studies, or there's some
something
like,
years.
research
5 petabyte.
behind
Yeah.
And
to
yeah,
try
we
to
have an
downscale it,
estimation in
also
a couple
with
of
some
years it
such
will grow
AI
up to 50.
applications, for example.
So times 10.
Yeah.
But
Yeah.
I
This is amazing.
couldn't
Yeah,
now
this is
review the
amazing
details
amount of
of
data
what
that
are
are
the limitations or
trying
what
to
is possible. I just know that like there are some papers out of it
Equal
which you could have a look at.
Yeah.
Is that
Because
right?
Yeah, well, choose another one.
But we're going to have to,
Yeah.
because we're not going to have to move it.
Yeah.
I don't know what
This is
the
management.
I mean,
On certain ratings, it's
how
data from users.
Yeah.
This is not
No, it's not.
It's not correct.
No, it needs to.
more
You will have
algorithms or whatever,
Yeah.
so
We need to.
why?
Yeah.
If you know
Absolutely.
something,
We just
I mean,
focus
some
on you
research,
Mhm.
manuscripts, please.
Yeah. Okay.
So we can access
Yeah.
all of data.
Thank
We
you.
can do
Yeah.
like a huge archive. We can access
Just as soon as we figure out who to pay for it.
Well, for current,
No, no.
sustainable goals and the green transition, it's very important to show the effect of reduction, so these kinds of things.
Yeah.
And
And you need it really at more local level. Yeah. So yeah.
All right, perfect.
Yeah.
I don't know if
I don't know. I tried to replicate it. No, it was quite long already last week when I saw this
got about 10 more minutes before we do our feedback and wrap-up session. So if anyone has any questions about any of the notebooks, then give me a wave and I'll come and say hi. Oh, is there a problem? Oh, we got. Just give me another account. If he's got a bad worker.
Yeah, maybe.
I'm trying to
Just check the notebook and how long it should take.
Oh, this is one of Julie's ones. I actually don't know, but hers are faster than mine. So, like 3 minutes.
No, it's taking a bit more.
stick.
I checked the nodes. The nodes are actually doing something, so.
So maybe.
There was a close here. No, no, it's just restarting the client.
And certainly.
I'm not sure. I'll have to ask Julia because this is one of her notebooks. I'll check in a sec.
Maybe it's a computation, I don't know.
No, it's just loading the cogs.
No, all the other are working.
Just this one. Okay.
Yeah, Cosmo.
Maybe we can
Okay.
just,
Probably.
we can shut down everything and try to load it from scratch again. Sometimes it just. This is Python. Yeah, it's Python.
I'll grab her as soon as she's finished that conversation. Still up. Woo. Julia, do you have a moment? Francesco's having problems running the 2_3.
No.
Oh no! Oh, it's done it.
Ah, no,
Okay.
it takes just like
Ah, six-
some,
ah, 6
because
minutes.
it's,
Yeah, yeah.
it's quite a few data files.
Look at that! You came over, it went and it ran.
Yeah, because we were restarting that process over and over again because I thought it's stuck or something, so I just logged into workers and
No,
clicked
no, we
calculation.
just
No,
we just
no,
load
okay.
14,000 data files.
Oh, okay. Cool.
But it's good that we can actually load it, right? So
Yes, it's incredible.
Yeah.
Here we go. And go desk.
Can you explain a bit what the different colors mean here in the task string?
Just different functions. I'm not sure if they're ever mapped. It's just
You can hover your
Yeah.
mouse pointer to.
most of these are all open rasterio. Nearly all of the big ones are opening natural data. Then there's some chunking and evaluation a bit. Add, I'm assuming, is just this. I think at the moment this is doing a standard deviation calculation. So probably do 2 passes, do a mean, and then do the delta from the mean in the second pass. So add's probably just making the mean. Yeah, so it made this standard deviation, so we can see the variability in the sea surface temperature in the Alboran gyre. And now it's gone to get a load of CCI and AVHRR data, C-time series, and it's gone mental. On, yeah, 8 workers, 4 EUMETSAT, 4 WECIA. I need to make more SLSTR cogs. I want to find a better use case example for this one, but this is nice. There's a really nice one to be made around deep water formation that I want to do, but I don't have the winter time period when the Mistral usually blows. And then I'll bring in ASCAT data too. the moment, I'm not sure I've got enough data available to warrant it. I think I need something truly massive to do that. And I think 4 times 8 gigs probably at the moment is enough for me to not hit any sort of limit. Yeah. Because if I'm doing a mean, then I'm doing it on, it's one process. I need to find a task that works on an image by image basis. And then, well, basically, go ahead, make a climatology and give me the anomalies of these, of the entire Sentinel-3 SLSTR record, because it has to do that 30,000 times. So then I think we can test. It'd be good to see though, because that's a task that's fundamentally impossible. Like without this sort of approach.
Yeah, so if you go, because it takes a while, so it takes around 6 minutes today, it took 2 minutes to weekend, but if you go, sorry, did this, okay. But, okay, maybe close your task screen and open it, because this looks stuck.
function to data frame is a trigger to start the workers.
Yeah,
And
so
then below is an example how to actually do it with the data proximate part. So this means we only use the X array as a function, then we compute it, and then we transform it to a data frame.
yes. So you do the clip. So yeah, okay.
We do the clip, and you just create the average over latitude, longitude, and this is lazily, so nothing
Yeah.
happens with
And you store it in this
as a
part of
function,
the
yeah.
compute.
Yeah, and then just with compute, we say, okay, now you can do something.
Mm-hmm. I see, yeah.
And but the difference is that now we only use the workers which we assigned at the beginning to our data proximate part, because Z5P is on BQ,
Mm-hmm.
and we just say that please use only the workers that are closest to our data. As Ben said, and as you also saw in the benchmark, is that the hub is still inside the EUMETSAT system, and so basically you don't see big differences between data proximate and non-data proximate in the hub, but you will see big differences if you do it locally.
Okay. Mm-hmm.
Because now the 4 workers have to compete against 8 workers, which is a bit unfair.
Uh-huh. All right. Yeah, that is.
And then you have to basically the time series to get the carbon monoxide averages over 2 months over Canada. It's actually the same, just like these 2 different, one's non-data proximate, the other time
data, and that's why it's not making a big
Yeah.
difference. But we have one calculator which is 5 if you people don't really want to see that, we can actually show it.
We don't have time now, I don't think.
and
But
then exactly, and then
I mean, essentially, my computer is a hub that's very far away. So that's why I did that orange graph. I think I've got it up here at the moment, but the orange graph is, I mean, and when I ran the orange graph, I threw quite a lot or comparable resources from my laptop at it here. I think I threw, I wrote here somewhere what I actually used to do it, but it's like 4, it's the same as we've got workers, it's 4 workers with 8 gigs per worker. And yeah, at best, at small jobs, 3 times slower. When you get to medium-sized jobs, we're 10 times slower, and that non-linearity implies that at some point, yeah, when you get to very big jobs, it will just be 100 times, maybe even not feasible. Because, you know, so much data, I'll die before it completes. Okay. Okay, I'm sorry to say we are coming towards the end. We've only got 15 minutes left before we hit 12:30, and for the last 50 minutes we've only got 2 things. We've got open session for questions that you might have, and then we've got our feedback form, and then I'll tell you how to contact us and where to find some of these resources. So, first things first, questions, open floor, anything you want. Anything you want to ask us about anything today, about the data, about the access, about data proximate, about Dask, go ahead.
So all these Jupyter notebooks examples, is there a Git repository?
Yes. Slide after next. All publicly available. Everything that we write for our training courses that Julia and I write for atmospheric composition and marine is all open source, all shared through one of our 2 GitLabs. One GitHub, one GitLab. I'm going to show you where this one is, but I'll show you the other ones are too.
Because in one of the introductory slides, it was written in source, but it was also in brackets something like Zoom or something like that.
Oh, did I? Okay, well, all the notebooks are available at MIT open source. Yeah. Yeah, so all of the notebooks are there. What we're also going to add is a lot more on how the actual cluster spin up occurs as well. So that was the part that we were referring to as soon. Because at the moment you have the notebooks. All of the notebooks can be run locally on your system if you want with Dask. So if you just want to explore Dask for working with this data, you can do so. We're having a conversation in the background at the moment about whether or not we can leave this system up for a little bit longer so you have a chance to play with it. I have yet to get a categorical answer, but I'll let you know if I hear. But the part we'll add is the part on more of the infrastructure side of things. At the moment, that's not quite so publicly available. So.
The slide will be available on this website. The slide, yes, this one.
Yeah. Well, I assume so. I mean, they've recorded this whole thing, so I'm guessing so. If not, the QR code is at the very end. I have all your email addresses. I can send you the link to the PDF version of this presentation directly if you prefer that, just to remove any ambiguity. Okay. Anything else? Okay. Well, Julia is around tomorrow, as am I, and I'm also around on Wednesday and Thursday. So if you've got any other questions you suddenly think of, then by all means come up to me, say hello. You can reach us both at the email address I'll provide at the end. And maybe I'll just skip on then to the next part of here. Feedback. Very, very short form, 5 or 6 questions. Access it either through that URL or that code. It will honestly only take you like 30 minutes, or 30 minutes, 30 seconds. But without your feedback, then we won't really improve our training. So it's really valuable for us to actually get this information from you. I'll just give you a minute or two to do that.
We're working a lot with these temporal bands.
Yeah.
Can you also use it like to like an urban heat islands? What is the resolution of the?
So for the sea surface temperature product, it's 1 kilometre at the moment, but there are new development missions coming online that follow more on the Landsat TIR legacy to look at 10-20 metre infrared. It's very challenging to do because it's very difficult to compartmentalise a longish wavelength IR signal into just a small box that size. But I think Trishna, a collaboration between the Indian Space Agency and CLS or CNES are going to be looking at high resolution thermal. And potentially, I think, building on Landsat's previous experience, then there might be some medium to high-res stuff coming out from Europe under consideration, next generation missions too. So historically, it's a very hard signal to derive at high spatial resolution. But, yeah.
Do you think, I don't know, the Copernicus program or the European Space Agency in general are working with similar algorithm than the USGS used for Landsat 2 collection too, because now the thermal data is in 30 meters.
Yeah, from TIR. Yeah. The thing is, TIR didn't last that long, and lasted even longer in terms of high quality data. The problem isn't a data processing one. The problem is an engineering one. It's just physically, it's just quite a difficult thing to implement on a sensor. Is my understanding. So. But without high resolution thermal data is extremely useful, both from an urban perspective, from a land perspective, and also for myself from a coastal oceanography perspective, to have that information right up to the coast to look at things like outflows of plumes from various things. It's really good to have. So there are, I believe, some backtrackable algorithms that use things like in situ sedimentology, like TSM and stuff from Sentinel-2 that can get some of this information. But it's not very easy to do, and that's only in a marine environment.
Well, it's even worse with passive microwave, of course.
Absolutely. Yeah. Though you don't have the attendant cloud issue. Yeah.
One last question.
Oh yeah, sure. Please go ahead.
Can you gather information for the oceans, for example? How deep can you get information concerning the temperature?
Concerning the temperature, infrared measures the top 10 micron, and microwave measures the top centimetre or so. Everything beyond that for thermal has to come either through in situ or numerical models. We can get a lot more information deeper from optical, and we can get full depth for altimetry depending on the nature of the circulation. But, yeah. Okay. That is us coming to the end. That QR code will take you to this presentation, but I will send it out to all of you anyway. I hope you found this enjoyable, informative, a good start to the conference. We run a series of training courses throughout the year, covering various thematics. That includes weather, climate, atmosphere, ocean. You can find our training calendar online at trainingevents.eumetsat.int, or you can email us at ops@eumetsat.int if you want more information on anything specific. We're starting to develop our calendar for 2024. We will be around quite a lot, running our own events, also at various different conferences. If there's anything in particular you are interested in learning about, and you say, we really need to have some kind of short course on this in particular, then by all means reach out, let us know, and we'll see if we can find a community that's big enough to warrant running something. Access to the resources from today. This GitHub, github.com/wekio/multicloud, will take you to, and I'll bring up the page. Oh, hello. We'll bring you to the GitHub page where we stage everything related to our work on the Wekio cloud platform, including today's work. I'm logged in as Wekio, so I probably shouldn't be because you'll see everything. Oh, hello, no, it's gone away. Apologies, let me just fix that. Okay, only 3 weren't public. Multi-cloud is where you'll find everything from today. All the Jupyter notebooks from today are stored under multi-cloud. Now, this is just the stuff that we do for Wekio, so the Copernicus stuff. You will also find, if you just Google the word EUMETLab, it will take you to our EUMETSAT specific GitLab instance where we have all of our training code available for all of our stuff, be it Copernicus or non-Copernicus. So here you can see we've broken down by thematic, weather, oceans, atmosphere. Look at atmosphere for an example. We have loads geared towards using sensors, specific applications for dust and fire monitoring. Under oceans, under ocean training, we have repositories geared towards working with any of our sensors. So anything aboard Sentinel-3 or Sentinel-6, there's a specific repository for working with that data, along with the information on working with our OCSAF catalogs, which the AVHRR data that we work with today is from. There are also some applications in here as well. This is ever growing, including case studies about marine heat waves, harmful algal blooms, anywhere where we use our data in terms of like a practical purpose associated with something. So I will post-event email you both the presentation or link to the presentation, the GitHub and GitLab address, how you contact us for more information, and where you find our training calendar. If any of that looks useful, reach out. If you have any further questions, reach out. We're always around to help you with our data in any way. So other than that, look forward to seeing you guys around for the rest of the week. I hope you enjoy it. Thank you.